Okay. Welcome back, everybody. Apologies for last time my camera shut off. I hit the magical button on there that said shut off right in the middle of whatever I'm saying. So I had come back to record the lecture, kind of comical. And I get in the conference room, if you guys got to see that. It wasn't nearly as good as class, so there were a lot of lessons to be learned. Like we had a good interaction over what should happen in the interval test, and I really liked that, and I was kind of excited by the class, and I was like, this is a good punchline, you know, whether you caught it or not. And then, of course, my video wasn't there. So when I went back to the conference room and I tried to record it, it shut off after 10 minutes again. So I hit some magical button in the morning, and I don't know what I hit. So I reset my camera to the default settings, and it seems to be working right now. I really hope that it is. So it's something I did. Anyway, apologies about that, but I did learn a lesson that in-person class is just a lot better, you know, one way or the other. And so whether or not you're the one that's interacting, just being here and getting something out of it. So I felt talking to myself wasn't nearly as productive. Anyway, what I said was stuff about the interval test. And I said the p-value for the interval test, testing if something's in some interval. If I wanted to know if something was outside of the interval, 1 minus the p-value isn't that corresponding p-value like it would be in the one-sided test. So that means it's not additive. The two spaces don't add up to 1. They're not measures of that space, the p-value. P-value is just error control. And so if it ducks alpha, so alpha is the big deal, and I can understand why people are like, I don't want to just set alpha and then I can't budge it. You know, that's cheating, they tell you. So I sympathize with Fisher. I think the interval test for the Bayesian is a real highlight of maybe what we should be doing. And so if you look at the posterior probability for the null hypothesis, theta is inside the interval. If I wanted to know what's the posterior probability that theta is outside of the interval, it's 1 minus that posterior probability. They add up to 1. It's a probability rule. So the p-value is not a measure of the hypothesis. And in fact, the p-value means nothing. It's alpha, and it's whether or not you reject alpha, and either you do or you don't, and alpha is your control on the type 1 error. And if you set everything up right, you'll be uniformly most powerful. And if you want to know more about that, you can take an inference class. I think that that's a compelling example. So the Bayesian's answer is elegant to me. It's like it's so simple, it's so straightforward, you just integrate the area under, you know, in that region, under the posterior. Simple, straightforward, makes sense, intuitive, has all the properties that I want it to have. The one-sided tests, the Bayesian and the non-Bayesian, have a correspondence with each other. And so those measures tend to be additive. If you like to think of your p-value as a measure in that case, I don't see why you just don't become a Bayesian at that point. And you get the interval test for free. The sharp test is the contentious one. And I don't think it's because you're being a Bayesian or a non-Bayesian. I think the question is flawed, where it's like I'm going to compare a point to everything else. It doesn't quite make sense. So you have to do all this reweighting of the spaces, and for Bayesian, that's a point mass prior, and I have to stack mass on that space, and it's a question of how you stack mass on the space. Of course, stacking mass on the null hypothesis is a relative thing compared to how you're stacking mass in the alternative space. And that's the real thing that matters. But I think that's a contentious test simply because the question is so, like, out there. Is it this point or is it anything else on the spectrum? So I think that question is flawed. But if people want to answer it, I think you have to do it in a comparative sense. So I think the Bayesian wins there, but it's still not an easy thing to like conjure up how you deal with the problem. Stephen?
Yeah, I was thinking about that yesterday, and you talked about how a lot of it depends on phi.
Yeah.
And
it was psi, right?
Sorry, yeah. And you had said that as psi goes, as you increase psi, so you blow it out, it puts more weight on the null.
Yeah.
Is that it?
Yeah, so think about it. So again, the point mass prior. So this is what we're talking about. It looks like this. So I'm going to end up putting some mass on theta naught. So I'm going to have a delta function on that, and then the alternative is going to be calibrated by this psi parameter right here. So again, the prior on whatever it is we're testing, I'm just going to call it theta in this case. Theta is equal to pi naught, delta theta is equal to theta naught, plus 1 minus pi naught. And I'm not going to put the indicator that it's not theta naught because I'm going to use a continuous prior. And integrating under that point has 0 mass. So this is going to be normal. And this is, of course, over theta, and it's going to have parameters theta naught and psi right here. So this is what that prior looks like. Think about if I end up making this bigger and bigger and bigger. So what this is going to look like, psi big, is going to look like this right here. So I'm not going to make it infinitely big yet, but I'm going to make it bigger. Let me make it. So this is supposed to look normal, and it's coming down. So think about what I just done is if I kept this pi naught the same right here, now I have a lot of mass on theta naught compared to this little thin region where I'm blowing out this mass that integrates to 1 over the whole range. If I take this out to infinity, I'm really squashing that really far down, so I'm placing very little mass on every other point in the alternative space. So in the comparative sense, theta naught is getting a lot more mass, and when you take psi out to infinity, you place infinite mass on pi naught. What do you mean? It's not. The point mass is staying the same because I'm not changing this over here. These are the same. So this point mass is not getting squashed down. It's just that the relative height of the alternative is getting changed. So again, all I'm changing is this thing. So this is the important quantity. This is where all your questions should be aimed. So I think this is really what I intuitively think about is in some probabilistic sense that's calibrated the distance I need to be from theta naught before I'm willing to reject it. And so in that sense, if psi is infinity, then I need to be infinitely far from theta naught before I'm willing to reject it, and you get the paradox there. Can't. So that's what's really happening. There are other priors that try to deal with the rates. So you could say, hey, some of my questions should be here. I'm not going to buy into this book that was written in the 90s, you know, and say that it doesn't matter. It does matter. And so it controls the rate of convergence as a function of the sample size. And there are these non-local alternatives. I usually tell people, use Cauchy tails, regardless of what you do. Jim agrees with that. Lindley agrees with that. The horseshoe guys agree with that. So on and so forth. So maybe Cauchy tails is a better thing to do. But in any case, you can analyze this specific form and kind of see at least what the behavior is. And so this is a very sensitive tuning point. It's setting up your comparison. And I think a lot of people don't understand the math, so they're not thinking about it. But really, it's compared to what sort of question. So I think it's fascinating. I try to avoid this question, but in this context, I really can't avoid the question. So I have to do something. You know, if I'm going to be pushing variables to 0, I need to understand how hard I'm forcing them to 0. And so we do apply point mass priors to all of the data, so that's where we're going with this. We're going to be studying this problem, y is equal to x theta plus epsilon, where this is a vector of y's, y1 down to yn. This is my design matrix. So this is going to be x11 up to x1p. So this is going to be the dimensionality of the problem. These are the number of covariates, p. And this is going to be xn1 up to xn2. And these are all filled in. And then I'm going to have my betas. Beta 1 down to beta p. Again, a lot of people take the first column and make them 1s so that this corresponds to the intercept. I'm not going to write that in as alpha. I'm just going to leave it as beta 1. And then you have your errors. So this is going to be my normal error right here. So these are going to be error i's are going to be normally distributed with the same variance. And if you don't like that, and you have different variances for different parts, you can do that. You can add it in. You can do the generalized linear modeling thing. But these are all your errors. Right there. And so what we want to know is, basically, are the betas 0? So model selection really is hypothesis testing in some sense. It might be very formal. Like if we apply point mass priors, then I'm going to need to think about how I calibrate everything. So the point test is usually what people are interested in because they want to get rid of the betas in their model, make a more parsimonious model. So this is going to be the beta j's are equal to 0, or there's something different. And so formally we can apply point mass priors, but we're still going to have to, if we use this framework, and we place priors like this, I'm going to say beta j is equal to 0. This is going to be centered at 0, but I'm still going to have this for each one of the beta j's, and I'll need to say something about it. And so the very typical thing that people will do is they'll do the same stuff that you do in any regression class. Is we usually check for multicollinearity, throw that stuff away, and then maybe normalize everything. So we'll take all our x's and normalize them so they have the same contribution. If I teach a Stat 101 class, that's probably the #1 question you're going to get is, how do you normalize? When do you know when to normalize, and how do you, what is the normalization? And there's no good answer to that question in general because it's how do you want to compare all these features to each other? So it depends on what you're doing. And I've had funky normalizations in here that make sense in the context of a problem. And sometimes I just do this typical thing where I subtract off the mean. Where the mean is going to be if I just sum these things up right here and I divide by the number of observations, I'll subtract off that mean, and then I'll compute the standard error for each one of those, and I'll divide by that. So basically, you come up with that z-score thing, and you plug that in. And so then that maybe we have a little bit of hope that maybe we can take this thing and make it 1. And so you're kind of saying if I'm 2 standard errors out, at least probabilistically, you have a good chance of rejecting. It's too bad that it just comes down to that, and it's like you're just so tempted to do the auto procedure, but I think you should stop and think about it all, what you're doing. I like this framework better than any of the other frameworks because at least it makes me think about things in a comparative fashion. And so it forces me to do everything. There's an MCMC approach for cycling through this and figuring out what the posterior probabilities of your null are. It's going to be hard to work out analytically because you've got all your other betas in there. So testing just each one of the j's, beta j's is equal to 0. I have all my other betas and all that other controlling and conditioning, and it's correlated with all that stuff that's associated. So you're going to set up a GIF sample and cycle through everything. That's called the stochastic search variable selection method. And I'll be walking you through that when we get back, and I'll ask you to code it up. I don't know, any other questions? Kind of just as we're talking about point mass priors and what the issues are. I'm not going to be able to make the issues go away, but I think the real reason all these issues arise is because the question already is kind of weird. I wish people would test the interval. But of course, you're going to have to explain why you picked your endpoints. And your endpoints of that interval are going to really be it's going to matter. So, and I like it because it's less elusive than that. Right there. So some people have done things where they've said, I'm going to place not a point mass, but I'm going to place around theta naught for my null hypothesis. I'll pick something that's really tight, compared to something that's diffused. And maybe you can compare those two variances. And maybe that means something to you. So that's called spike slab. So is what people call this prior. And the point mass is the limit of spike slab, where you're taking that variance and you're driving it to 0 and everything and just making that a point mass. People studied this problem for a long time in the 90s, and they said, spike slab, maybe it gives you some interpretation about the ratio of the variances. Maybe you like that, but ultimately it's almost equivalent to using point mass. So it really doesn't matter if you do that or not. Again, everything is comparative, so setting up the right comparison for the problem at hand is the name of the game. I'm going to be giving you data where I'm going to be simulating my x's, and I'm going to simulate my y's, and I'm going to know how I simulated them. And I'm going to know which x's I put into everything, or what the betas are. So what I'm going to do is I'm going to simulate a bunch of x's and a bunch of y's, and I'm going to simulate some betas as well, but some of them are going to be zeros. And I'm going to know what they are. I'm going to give you 3 different data sets. I'm going to give you one data set where all the x's have nothing to do with each other, so they're independent of each other. When I create them, I'm going to give you large N and relatively small p. So p is going to be like 10, and N is going to be something like 1,000. And all of you are going to get the right answer. All of these different methods are going to virtually agree. Fairly simple problem. And if you're a classicist and did something, you probably stepwise selection or something like that, you probably get the same answer too. And then I'm going to start doing other things. So I'm going to maybe let the x's be a little bit associated. Maybe I plug in too many x's or something like that. And I still know what the generating model is, and I'm going to ask you to figure it out. And you're going to apply all these different techniques. And you're all going to get slightly different answers. And you're going to want to know which one is true, and can you ever figure it out? And the answer is probably not. So I tend to think it's reasonable that maybe you're able to figure out about 80% of the betas, or something like that, which ones are the right ones that are in the model. So what I would encourage you to do over the break, since I'm not giving you a homework right now on this and extending the homework, is build a simulator where you're generating x's and y's, and then play around with these schemes and see, you'll know what the truth is, and see how well you do. I think you'll be surprised. And if you end up changing the error structure, maybe you end up doing logistic regression with all of this, you'll do even worse. So I tend to think that being about 60% right is pretty good in those cases. And I've sat down and run my own simulation studies and convinced myself when people come in and they say, I get it right 95% of the time. I usually think, okay, you've set up all these other methods to fail, and there's something special about the way you've generated it that your method works well. And so it really is just a question of how sparse are the betas. Do you just have a few of them relative to p, or do you have a lot of them? And so methods that work well where you have sparse situations don't work well when you have dense situations where there's a lot of betas that are active. And vice versa, because it's all about this penalty of how hard you're pushing on them. And so we're usually arguing over that. Difficult thing is, you don't know in reality. It's like, are there just a few betas that are going to explain everything versus a lot of betas? So a lot of times people will remove the inferential side of it and just think about their predictive ability. How well am I able to predict? And I'll give you an answer that does that that's relatively parsimonious. These all do that in slightly different ways. So everybody in the world that has a PhD in statistics has their favorite model selection techniques. And if they write papers on it, they usually don't tell you the downsides of it. And every single one of them does have a downside, because it's an artificial question. This versus that. Anyway, let's get to it. And let me show you some things that people do. Let me just pull you real quick. We've all heard of this. We get the idea. I'll show you how to implement the Gibbs sampler when we come back. Who's heard of ridge regression? Most of you. So, and I'll try to convince you, you've probably heard of it, even if you haven't heard it called ridge regression. Who's heard of LASSO? Really popular. these days. So, and I'll show you kind of, they're very similar to each other, but they act very differently. So the at least basic setup is similar, but they're pretty different. Who knows what this stands for? Least absolute shrinkage selection operator. Shrinkage selection operator. What's the idea here? Why do they call it the lasso? They're being cute. So they think that it's like a lasso that you're swinging in the air and you're going to go throw it around something and tighten it and shrink that thing. And the thing that they're alluding to is somebody's neck. Okay, no. It's supposed to be one of the betas. So it's a little bit crude of a thing. You'll sometimes hear this called at different universities the lasso. And that comes because Trevor Hasty, which is one of the people that are responsible for this method, is from South Africa, and he calls it the lasso. So I found this fascinating when I was a graduate student. So I had heard everybody calling it the lasso, and I remember doing problems and going, isn't that word lasso? And so I was in school in California where Trevor Hasty was. And so he walked around, he called it the lasso to everybody, and everybody without a South African accent is calling it the lasso. And then I went to school in North Carolina, and everybody was calling it the lasso. And I couldn't figure it out. Like, what is that? All these, like, people like me that grew up in the States calling it the lasso. And so I'm putting this twist on it, and you'll still hear that sometimes depending on where you're at. So these were early purveyors of the lasso that were talking to Trevor, and Trevor's calling it the lasso, and so they call it the lasso. I had a really cool experience when I was in grad school that I took a teaching position for about a month in South Africa. And when I started going through this, and I was calling it the lasso, people were impressed that I was calling it the correct thing, because they had heard lasso. People say that, and I finally figured out where it came from, that that is the way that they say it. So it's the lasso. So, and if you think that the metaphor is really crude, that you're throwing around something and giving it a tug, there's a precursor to this method that's very similar, a little bit different. It came up earlier, and it's called the garrote, the carrot. Do you know what that is? You guys know. Pretty twisted that you guys even know what this thing is. It's a torture device, right? So where they put this pressure on people, pop, you know, tell us what you know. So every time I hear that people talk about this thing, I'm like, we really need to change these things. But lasso is a downgrading from how morbid the garrot is, or the garrote, or however you want to say it. I'll show you what this is in a second. We know what this is. So least absolute shrinkage selection operator is where that comes from. Okay, let me show you what this is first. So ridge regression. I'm going to show you the classical form of it. So, and this has been around for hundreds of years. So people can do this analytically and write down the solution on the board. And it's kind of a good precursor, I would say, to doing model selection. So ridge, the typical, the non-Bayesian formulation and I don't remember how to spell this, but this is like, I'm not gonna try. It's called Tikhonov regularization. And so when I was studying computer science back in the day and doing a lot of optimization, we called this Tikhonov regularization. So Tikhonov, sorry, I don't remember how to spell your name. But I'll try. No, I don't want to try. So, not in a spelling mood this morning. So when I saw this pop up later on, I was like, oh, I know all about this thing. But I had learned it in a non-probabilistic fashion. I had learned it is this basic problem. So it looks like this. So we want to minimize this thing, y minus x beta in the 2 norm. So this is the squared error norm. What I really mean by this is y minus x beta transpose minus, or times y minus x beta. So this is squaring everything in some sense, so that's the 2 norm. I could throw a half power on here, square it, it doesn't matter because square root is a monotonic function. So sometimes you'll see people write the half power in there. So, but basically we're just looking for the squared residuals. So this thing right here is just equal to sum of the yi's minus xi transpose beta squared. And so this is going to be I goes from 1 to p, or this is n. So I'm just taking the squared residuals. This thing just reminds you x transpose beta is just going to be the sum over, I'll say j goes from 1 to p, xi, j, beta j. So this model over here can be written out as yi is equal to sum of the xi transpose. So what that is right here is just these columns. And then I'm going to be multiplying them by these beta j's. These things right here. So this one times all of that. And I'm adding it all up. This is all just a series of dot products. And so for this one right here, y1, I'm going to multiply that by that, and that's that sum. Plus air I, and I'm going to do this for I goes from 1 to n. So I'm going to have all of these. And then I'm going to figure out what my beta j's are that kind of fit this pattern. And so you might be thinking about minimizing the squared residuals, and if you're one step ahead and thinking about a likelihood function, you're doing something equivalent. Jim? Yeah. Oh, sorry. Not transpose here. This is xi transpose beta. Thank you. So minimizing the squared residuals right here. This is the typical thing people are doing. We know the solution to it. It's up there. So x transpose x inverse x transpose y. So that's the solution to this, where I'm going to minimize this over beta. A lot of times people put the hard minimizer is going to be your beta hat. And so sometimes this solution doesn't exist. For one thing. So if p is greater than n, this solution won't exist, i.e. x transpose x inverse won't be invertible. So x transpose x is not invertible, so the solution doesn't exist. If the x's are multi-collinear with each other, i.e. they're correlated, so perfectly correlated, so if one column is a linear combination of other columns in the matrix, then this solution won't exist. X transpose x won't be invertible. And so you can penalize this. And so this is going to be subject to a constraint. So subject to. And it looks like this. Sum of the beta j's, j goes from 1 to p, is going to be less than some constant. So this is going to be some penalty right here. So this is going to be a constrained optimization problem. And this is what ridge is, or Tikhonov regularization. Oh, I messed up again. Squared. So that everything's positive. And so this is going to be some positive value. And you can think about what this does. If I make C smaller and smaller and smaller, I'm going to be taking this sum and essentially its contributors to the sum, and I'm going to be trying to shrink them towards 0. So I'm going to be smashing them. So I'm smashing them in this big joint fashion like here. I've heard arguments where it's like, that's just a bad idea to do it all at once like this. And it's an okay idea. It's not too bad. This has another formulation. I can rewrite this. So rewrite. This thing as arg minimizer over beta. And I'm going to throw this thing in here, y minus x beta. I'll write it like this, y minus x beta. So basically just the 2 norm plus lambda sum of a beta j squared. So this beta right here is this whole collection. So beta 1 to beta p. I could rewrite this is the arg minimizer, if you'd like, over beta of y minus x beta. I'm going to write it in terms of the norm notation. 2 norm plus lambda beta 2 norm. Right here. So this thing right here is just beta transpose beta, is what that is. Sum of squares, quadratic form. So does anybody know why I can switch from this to that? Lagrange, yeah, thank you. Thank you for showing up. So and filling us in on that. That's a Lagrange multiplier setup. So this is the thing you learned in calculus class where you take your constraint. There's a little bit more to it where I'm going to build some slack variable in here, but it's a Lagrange multiplier equivalence. So this is the Lagrange multiplier right here. It's not C, but it's related to C. So lambda is related to C. So whatever the solution is here, I can pick a lambda that matches that solution. They're not the same numbers. And we'll see a little bit of this correspondence in a moment. The Bayesian has a slightly different setup on this.
Are you saying then that the constraint equation is the sum of the bj is less than C?
Yeah, so this thing right here is again just beta transpose beta, so I've got this constraint. What do we do in Lagrange multipliers? We introduce this new variable and we add it in. Lots of interpretation here, so that you can think about it. And if you know a lot about optimization, you can save probably several hours worth of stuff about this, what the equivalence is and what the interpretation of that is, and the correspondence to that. So I'm just telling you that there is a correspondence as it comes through Lagrange multipliers. I took an optimization class a long time ago and I learned about slack variables and shadow prices and the dual to the optimization problem. And if you know all that stuff, that's cool. So there is a relationship here. But I'll just leave it here. So this is Lagrange multipliers. So what this says is if I make lambda bigger and bigger and bigger, I'm adding this thing in. So I'm trying to minimize this, so I need to shrink the betas. So large lambda relates to small c in this. So again, I'm trying to minimize this thing subject to that. So if I put a lot of weight here and this is all positive, then to bring this thing down, if lambda is big, I need to make the beta small. So it's acting as that penalty. There's a closed form solution to this problem, and you can work through it. Keep in mind, everything is in the quadratic form. I'll probably ask you to do this for homework, but you can just work through some derivatives and figure out the solution to it. We'll do it in the Bayesian fashion. We come up with something very similar to this, just by looking at the posterior distribution and looking at its mean or its max or something like that. So the solution, I'll ask you to do this probably on homework, is going to be beta hat ridge going to be equal to x transpose x plus lambda, same lambda that I've written over there, times the identity inverse x transpose y. Very similar to what we have up there. And so again, you can check all this by working through your derivatives on beta. When you take the derivative on lambda and you try to solve that system, you're getting back this constraint right here. So when you do a partial derivative sort of thing, set everything equal to 0 and solve for everything, you get that, you recover that constraint right back. Okay, so this is the ridge solution. And this always exists. If lambda is greater than 0, this thing is going to be full rank. This might not be full rank right here. This will be invertible because I'm adding it to something that's full rank and everything is positive in there. So if lambda is greater than 0, this solution exists. And I guess some people have thought, just because of the existence of this solution, it's a good idea. And so it's called ridge regression. And we'll see this in a moment, that if the x's are, if x transpose x inverse is not invertible, the likelihood function will have a flat section in it. That's a ridge. There's an infinite number of solutions along that ridge. And so what does this thing end up doing? It cuts through that ridge and it picks one solution on the ridge. So that's where it derives its name. So let me show you how Bayesians treat this problem. It's very, very similar. So this is Bayesian ridge. And I should say that probably most Bayesians end up doing this by default. So this is going to be my likelihood function. So my step 1 is write down a likelihood function, beta, given x's and y's. Try to give myself a little bit more room. Try to remember that ridge solution. It's not too hard to just plug that into that equation up there. This is just going to be proportional to, remember what we're doing inference on is the betas. If I didn't know the sigma, I'd have to co-estimate it. I'm going to assume you know sigma, like I've been doing throughout class. So this is going to look like e to the minus 1/2 y minus x beta transpose times sigma squared. This is going to be, I'll write it like this, sigma squared times I inverse y minus x beta. This thing is just e to the minus 1/2 y minus x beta transpose y minus x beta. I personally don't like inverting the identity matrix in my code, so I usually just get rid of that. This is divided by sigma squared. So this is the variance of the original problem that we wrote down. So if I'm optimizing the betas, the sigma doesn't really come into play. If I were just looking for the maximum likelihood solution, I could end up taking a log of this. And this up in the numerator is the 2 norm. So same thing that we have written over there. And so if I were trying to maximize this whole function, it's equivalent to minimizing this. So again, E is monotonic. And then I have this negative sign in here that changes my mins to maxes. So same sort of thing. So that's just this component right here. So similar formulation. Bayesian gives you a little bit more because they're going to give you uncertainty using this and not just give you an answer. They're going to give you other possible answers, a distribution of answers. And so step 2 in my Bayesian analysis is to pick a prior, and the ridge prior is the normal prior. So, and it's going to look like this. Normal, it's going to be centered at 0. I'll write it out like this. E to the minus 1/2 proportional to E to the minus 1/2 beta transpose beta let me write it this way, beta minus 0, I'm centering it at 0, times beta minus 0. Everything's centered at 0. And then I need to talk about how much I'm going to enforce this constraint. And I'm going to call that psi. Psi is not lambda, it's not c, but it corresponds to it, at least with respect to what sigma squared is. I'll call it psi squared. So this is a normal centered at 0, where this is the 0 vector. And this is going to have this thing in here. So let's just see, and we'll see that we recover the same solution. So posterior is just the product of these two things. This is going to be proportional to e to the minus 1/2. I'm going to factorize that out of both of these. So I'll do my producting in just one step. And this is just going to look like this. Y minus x beta transpose y minus x beta. This is over sigma squared plus beta transpose beta over psi squared. So we're starting to see some sort of similarity in all of this. And so I guess I could mess around with this a little bit and throw this thing over sigma squared so it looks the same as over here. And so I have this parameter right here that's showing up in front of everything. So now I have everything divided by sigma squared. And so maximizing this is a function of beta. So maximizing pi beta xy is equivalent to minimizing y minus x beta transpose y minus x beta plus sigma squared over psi squared beta transpose beta. This ratio right here, and you don't know sigma squared, so I can just mess around with this and call this lambda if I wanted to. And how I control lambda is by controlling the prior variance. And that's the same as this thing over here. So Bayesian ridge is just using the conjugate prior. And my prior does matter in terms of how much I want to enforce those betas going to 0. I want to just point out that this solution is all right. Can anybody tell me geometrically, what is this shape? Think of it like this. It's a circle centered at 0. So it's this circular shape. So this looks kind of like this. So I'm going to call this beta 1, beta 2. And so this circle, and this is 0, 0 right here, is just tightening things up around here. I want you to see that this is a smooth function right here, and this is also a smooth function. And so if I'm optimizing using this penalty and everything is smooth, it's very unlikely that I'll stack mass at 0. So I might be compressing everything towards 0, but I'm not going to get hard zeros. And so here's what the LASSO is. Let me show you this. We'll come in and we'll pick up next time with this, and I'll run a few simulations and show you how to use LASSO. But LASSO is this sort of thing. So here's the old way of doing it, not the Bayesian way, but there's a Bayesian equivalent. So we're going to arg minimize y minus x beta to norm. and then I'm going to subject this to a different constraint. So instead of taking these beta j's and squaring them, I'm going to put the absolute norm on that. And this is going to be less than some positive constant. So these are all positive, so I'm going to enforce that to be positive. And so, same sort of thing, I can optimize this. I'll use my old thing that I wrote. Like that. So same sort of Lagrange multiplier setup. So this is equivalent to this. So there's some C that I'm going to squash everything down, and I can penalize this thing. This has an unfortunate consequence that I don't get to do calculus, because it's not smooth. I've got that absolute value sign, so derivatives are out. You need a computational algorithm to optimize this. I'll say a few things about it. I'm not going to teach you any of the computational algorithms for optimizing this fast, but there's something called least angle regression that this is equivalent to, and by doing that you can optimize real quickly. Basically, I'm going to teach you to go to MATLAB and just run the optimizer on this. So this is the non-Bayesian formulation of everything. Bayesians want a little bit more than just a point estimator. We're statisticians and we want uncertainties. I think that that's important. So the Bayesian version, Bayesian LASSO, is this thing. I'm going to take my likelihood function. So x beta, xy. This is going to be the same thing. E to the minus 1/2 y minus x beta transpose y minus x beta divided by sigma squared. And the prior that induces LASSO, there's a neat computational way of dealing with this, and I'll expose you to that paper. I'll send it out over Slack or put it up on the web page and you can read through it. I'm not going to ask you to implement it, but I think it's interesting. This is going to look like this. Product I goes from 1 to p, e to the minus, I'm just going to write it like this, lambda beta j. So this thing right here is called a double exponential. I've written down everything up to proportionality. It had a lambda over 2 sitting in here for the normalizing constant. But this is called a double exponential. I wasn't able to write this out using just the norm notation. I had to use the product to do it. But if you think back to the Rich thing, if I just wrote down all these independent priors that were beta squareds and I producted them together, we would get back that beta transpose beta. And this is similar in spirit. So this is my penalty right here. That's my penalty. It's not exactly, I should probably write it in as psi or something, because it's not exactly this lambda. I'm going to have to rescale everything in terms of sigma squared just to make that the same notation. But basically, there's some parameter right here in the double exponential, and double exponentials look like this. So e to the minus psi beta j. This is going to be at 0 right here, and it looks like that. And so let me just go back to this right here and think about what this shape looks like. What shape is this geometrically? Yeah, it's like a rectangle. So it looks like this. Tilted over here. So this is going to be my 0, 0. Beta 2, beta 1. And so what I want you to convince yourself of is optimizing things with a constraint like this. If all of a sudden I'm moving, if I'm doing well in my optimization and I'm moving up this line, I'll keep moving until I slam into that border right there. And so, and if you know about optimization and simplexes, you'll understand that. And if you don't, it just kind of feels intuitive that at least there's this sharp kink in there. And the Bayesian is amplifying it a little bit with this, and it's placing all this sharp mass right there. And so what it means is that the maximum a posteriori estimators for at least increasing lambda is going to start inducing actual zeros. So instead of looking at the mean of this, you usually look at the max, the map estimator. And the map estimator is going to be equivalent to doing this optimization. I usually just do this optimization and plug everything back into my posterior so that I can use whatever code is out there for all the other guys as well. Again, I'll show you a Gibbs sampling procedure that people use for this. But people like this because it makes hard zeros. And that's like, wow, the wow factor. And it's worth doing all the computation and not just working through the rich solution. Oftentimes I use these things in sequence with each other, that I'll use LASSO. I might feed that into maybe a rich solution or something like that, and I might feed that into my Gibbs sampler as a good starting point. You know, that they're all kind of trying to do the same thing. The SSBS algorithm, the thing using the point mass priors, is going to give you a little bit more because now I'm going to have correlation between the inclusion and exclusion of the betas. So they're going to be going in and out of the model, and I can see which ones are kind of related to each other. And so I think that that's good because I have kind of this joint model selection that's going on. And it's controlling for everything, where this is just a penalty. So saying that, I kind of like LASSO. If you do go to places like Harvard, they'll say it's terrible. It's all right. So it's not as bad as they'll make it seem. They just have some competitive methods. And this one got popular, and this is the one that came out of Stanford. Is why they were really fighting this. So it's true. I'll say a little bit more about that when we come back from break. So no class on Friday. I'll send you a few notes over Slack. And if you need anything, you know how to find me. So email or Slack. All right, you guys, enjoy. And I'll see you when we get back, and I'll get you to start using this. Yeah, exactly. I can't.
I was going to say, you can't.
Yeah,
in the 20 dimensions or whatever.
you get the idea.